So the second lesson in the sequence is about exponential growth problems. In the previous video, we sort of hinted at this idea that when there's a natural log involved in the solution to a differential equation, you often, not always, but often end up with something that looks like PERT, that formula that you've used in your math classes or you used in intermediate algebra or in math analysis. And so this video is going to be all about using PERT, and actually so is the next video. But I think the first question to answer is, when do we know to use PERT? And we're going to look at the next slide for that. There are sort of two ways that a problem can be worded. So one, if a problem explicitly states that a population or something is growing exponentially, that's an immediate indication that it's exponential growth, and so we're going to use some form of PERT for that. It may have different variables. It may be CE, CE to the KT instead of PE to the RT, but they're both similar. The other way is more of a calculus sense. What we sort of saw in the last video is that if you've got something that's growing such that the rate of change of the population is directly proportional to the current population, in other words, if dp dt is equal to k times p, if you have this differential equation, then we know that it's going to yield, the PERT, it's going to yield CE to the KT. So you'll see some problems that will say growing exponentially, and others that will say that they're growing such that the rate of change of the population is directly proportional to the current population. Or maybe instead of the word population, they'll say investment. The rate of change of the investment, the growth of the investment, is directly proportional to the current investment. If you see language like this, it implies that you're going to be using PERT in some way, shape, or form. So I have one example of that we'll look at on this next page. So suppose that you have a population of bacteria that's growing exponentially. So there it is. You see growing exponentially, immediately your brain should shift into, hey, I can use PERT for this. Just like I said on the previous slide, I could have written the sentence differently. I could have said the population of bacteria is growing such that the rate of change of the population is directly proportional to the current population, and that would also imply use PERT. So long story short, we know we're using PERT. There's three parts to this question. Part A is I want us to write the exponential growth model for this situation. So in part A, we know that we want to have, population equals CE to the KT. Now I know I keep saying PERT, 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 and now I use CE to the KT. Part of the reason is that I want to have this equal to the population, and so I didn't want to use P here. Right? So we need to look at our data. Our data here says that it consists of 3,000 organisms at 5 p.m. So that means that you have a population of 3 at 5 p.m. Now in the context of the problem, the best way to do this is to not say that time is 5. The best way to do it is to say, well, you know what? Whenever time is 5, whenever it's 5 p.m., let's say that time is 0. Let's just say that time started at 5 p.m. and say time is 0. Right? Then we know further on that the population will be 8.2 thousand. I'm just going to use 8.2 at 9 p.m. Now again, I don't want to use t equals 9. If my initial time was 5 p.m., and now I'm 4 hours later, it would make sense that time is 4. That looks a little bit like a 9, so I should probably make that more clear. Time is 4, right? So when the problem says write the exponential growth model, it basically means find out what the constants C and K are. P and E and T are going to stay in the problem, but C and K we can solve for. Right? I'm going to do this by plugging in these values that I have over on the side. So first, I'll use green for it. First, I'm going to use this information. Right? Population is 3, CE to the K, when time is 0. And you can see right there why it's so great to have time being 0. Because now I have 3 equals CE to the 0. In other words, 3 equals C. And that's exciting. This is like an intermediate result. I can now apply this back to the problem and have a refined sense that P is equal to 3E to the KT. I was supposed to find C and K. I found C. Right? How am I going to find k? Well, I'll use this information to find out what k is. Right? If that's also true, it means that 8.2 is equal to 3e to the k times 4. And now I just need to solve for k. And I'm hoping you guys remember how to solve some of this stuff. I know we did a little bit of this in the B videos, but not a whole lot of it. Eventually I want to use logarithms for this. So first I will divide by this 3. That'll give me 8.2 over 3 equals e to the 4k. Now this thing is in exponential form. It's e to the sum power equals this, so I can rewrite that in logarithmic form. I can say the natural log, the log base e, of the thing on the other side of 8.2 over 3, that should be equal to 4k. Then if I just divide by 4 and plug this into the calculator, I'll end up with k being 1/4 the natural log of 8.2 over 3. Right? So I did that ahead of time on my calculator and found out that it was 0.2514. Please, 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 please store this on your calculator. As soon as I got that value, I stored it to k in my calculator. Now that I have that, I'm finally ready to sort of answer part A. Part A had asked us to find the exponential growth model. My growth model started out being P equals C e to the kt, and then I found C and k, so the population is 3 e to the 0.2514 t. Now remember, this value here, on my calculator, I actually stored that to k. So when I plug things in, I'm not actually going to type 0.2514. I'm actually going to type k because I have it stored on the calculator. All this algebra up above is really important. If you struggled at all with that, please go back and look at that. Like rewind the video and check that out again. So yay, this way we're done with part A. This is the exponential growth model. Now that I have that done, I can go on and do parts B and C, which fortunately are going to be, I think, much quicker. Part B, I wanted to know what the population was at time 7, right? So I just take this model, P equals 3e to the 0.2514, and I plug in, actually, I'm sorry. The problem had asked, what is the population at midnight, right? Midnight is 7 hours after 5 p.m., so this is going to be when time is 7. So I'm going to plug in 7 here. And this is really easy. Just throw all that at your calculator, and you'll find out that the population is 17.43. Now keep in mind, what does that mean in the context of the problem? This 3 represented 3,000. The 8.2 that we plugged in earlier represented 8.2 thousand. So this 17.43 represents 17,430 bacteria. Right? So now we just have part C. That's the last part of this problem, and then we're done. Part C asked the question the other way around. In part B, we gave you the time and asked for the population. Part C said find the time. It was basically find time when the population is 20,000. Right? So how am I going to do this? I'm basically going to plug in P equals 20. Remember that P I've been measuring in thousands, so you don't want to put in 20,000. That would be when the population is 20 million. I just want to know when it's 20,000. So I'll plug in 20. So I take my exponential growth model, which was P equals 3e to the 0.2514 times t. Remember, this time I want to solve for t, so I'm going to plug in 20 here. And the steps after this are just algebra. If you're watching this at home, if you feel comfortable, I'd really recommend you pause it and walk through these steps on your own to make sure you've got the idea. Again, it's exponential, so I want to get the exponential part alone, so I'll divide by the 3. 20/3 equals e to the 0.2514t. Now, because it's exponential, I can write it as a logarithm. ln of 20 thirds is equal to the power 0.2514t. And then the last part is just dividing by this 0.2514. So at this point, we're totally in calculator mode. It means, practically speaking, you're going to be doing the natural log of 20 over 3 divided by 0.2514. I'm kind of using calculator notation there to make sure that you're comfortable with that. And in the end, what I ended up with was time being 7.547. Now again, what does that really represent? This really represents hours past 5 p.m. right? So this is basically going to be a little bit past midnight. Now, if you're interested, something that I did was I took this value and I said, all right, well, if I do 0.547 times 60, it'll tell me how many minutes that is, right? I did that and found out that it was 32.808, so about 33 minutes. So what does that mean in the context? It basically means that our time is 7 hours and 33 minutes past 5 p.m. So the final answer for this one is basically that it was 12:33 a.m. the next day, right? So that's our answer for part C. That's the end of this video. It was a little on the long side. The second video, the third one in the sequence, should be a little bit shorter than this one because we don't have all of the intro. Although I did sort of want... Sorry, I got cut off because I tried to go back to a previous slide. And what did I mention? Remember, this PERT process is used in two cases. I mentioned them earlier. One of them is when the problem says it's growing exponentially, and the other is when the problem says that it's growing at a rate such that the rate of change of the population is directly proportional to the current population. So remember, this process is used in both of those cases, and that's all I've got.